Okay, I think we can start. So now we move to Muon, Muon cooling for Muon colliders. First, we have a talk by David Neuffer about the demonstrator for the Muon collider. And then after, we will have a talk about Mu Tristan, which is a different idea for Muon cooling, Mu plus cooling.
Yeah, I just graduated from Fermilab last year, but at any rate, so since then we've had this P5 report, and then the National Academy of Science recommendation 1, the immediate creation of Muon collider R&D and et cetera, which of course is not supported by any funding yet. But at any rate, I'm sort of just go through a little bit of, at any rate, if you have better ideas for what demonstrators we could or should do, I welcome them. But sort of an overview, let's see, yeah, it kind of works. Do an overview of what demonstrators we need and maybe our initial plans or possibilities. There's actually, Fermilab does not yet really have a plan, but at least it's maybe time to discuss possibilities. As a side note, in the beginning of August 6th or so, there's a meeting of the U.S. Muon Collider collaboration, and some things like the demonstrators should be discussed there. So this is just sort of going through the scenario as it exists. I'm just showing some of the options we went through earlier because we likely will reconsider or change some of the details of this. But at any rate, right now we have a moderately detailed scenario for 3 to 10 TeV Muon colliders, starting from a proton driver, target producing pions, muons, cooling of muons, and acceleration. And in every piece of this, there's stuff that needs to be built or has to be tested to see if it would really work. And some of these demos may be with beam, and some of them, a lot of these things can be found without actually beam tests. I mean, one of the things we needed to start on, maybe continue, is how well can the RF work with the magnetic fields. And cooling, we want to do some sort of demonstration which cools by much more than it's been done before. And we'll discuss that later. Certainly something here that's of importance. Can we really build this multi-megawatt target and get it to work and have it capture pies and muons and cool them, et cetera? And of course, everything else, God, the magnets are hard, the RCS is hard against, and of course, various people, magnets groups, RF groups can work on prototypes. So far, we have had some demonstration of ionization cooling. At the mice experiment, we basically, where our first goal was to do a full cooling cell. In the end, we just had a hydrogen and a liquid lithium hydride absorber, and we demonstrated that the beam does cool as it goes through that. Phase-space cooling and transverse phase-space actually was 10% or so. Not a big effect, but it's the right direction. And again, in the Muon G-2 experiment, we actually implemented emittance exchange longitudinal cooling in the beamline going into the G-2 experiment and improved the beam density roughly by 10%, which gives us a few more muons in the ring, and it helped, but it's again 10% scale. We'd like to, and again, the plan is to go to some kind of demonstrator where we can both put in items of cooling hardware that are actually ones we would use in the cooling scenario, and also the goal would be to have a long enough section of cooling, that we get a significant amount of cooling, with sort of an initial goal is maybe instead of 10% cooling, factor 2 phase-space cooling as a first goal. CERN is actually has a fairly is developing a very specific plan for that. In the U.S., while we have this grandiose goal to build a muon collider, we actually have no funding or support for it. But if that materializes, we'll also develop demonstrators, and hopefully complementary to what the International Muon Collider. And of course, this does, these demonstrators and R&D would not be just in CERN and at Fermilab, but at other cooperating, collaborating institutions. And while we're here, I was thinking, well, there may be other physics goals we can address with some of these hardware or beamlines that we might develop for cooling, and maybe there's some overlap between things that, for instance, low energy symmetry or say lepton flavor violating experiments, or some of the other experiments that aren't necessarily high energy physics that could somehow have a synergy with what we're doing. So one thing we want to do is test out the cooling system. This is sort of a table with sort of inserts of what little bits of the cooling system are for various parts of it. The current baseline that's in the international collaboration document is it's a fairly long system with lots of, basically 14 different types of cooling cells, each of which kind of is absorbers plus RF plus magnets in a fairly repetitive structure, going to higher and higher field as you go down to more cooling, and then, at least in the current design, a final cooling system with very strong magnets and relatively short absorbers. And at any rate, at CERN, they're thinking of, building a specific one of these, that is a string of one of these particular types, and enough to get a significant amount of cooling. The one they're actually focused on happens to be this one. One of the reasons they chose this is they want to start with the higher frequency of RF, because they believe that'll be less expensive. However, it has to be challenging, so it has also fairly high magnetic fields, up to 8 to 10 Tesla, basically, there. And so it does have certainly challenging features. So that's, again, as a beam demonstrator, I'll just have I was going to put a side comments on the cooling scenario. It is significantly better than the map scenario we developed. It's another level of improvement. I would say it's not been, it could certainly use another round of optimization, looking at things like, actually, as it stands now, for instance, there's no matching between sections. You just take the beam from one end and dump it in the next one, and you don't even rephase it. Now, that's interesting because it actually still works. I mean, because you're cooling, the cooling matches the beam in. So yeah, you get some losses at the start of each section because you didn't match, but it still works. A disadvantage of the system, and it's partly because they don't match between sections, is losses are larger than they really want, so that's something we probably need to work on and develop. And the apertures are kind of smaller than you'd like to, so that's another thing. I think if we weren't using quite so high frequency RF, that would help. Any rate, so there's certainly iterations to be done here, but at least we've got a scenario that kind of works. Problem is, of course, with high fields, it's high cost. And if you look at things like this is the cooling system cost as a fraction of the magnet cost for the collider system as it is. And we're spending roughly half our magnet cost on the cooling, so that's a lot. I don't know the number that is in billions, but it's not small. It would be great to reduce that. But at any rate, to do a specific demonstration of one of these systems, you CERN is looking at a couple of options on the CERN site. And I think what they're focused on is using beam from the 24 GeV proton synchrotron. And they currently had a beam line, TT10, that was a possible use. And again, right now they're thinking of a location here, which is TT7 that goes toward the ISR, old ISR. It's using a tunnel here, and I think it's using a place where a demo LINAC for CLIC was located. And so, at any rate, so at least this one looked well. Now it looks like we're something that go to a more specific thing. So there's sort of this shows some of the detail they've looked at here. The idea is you have this beam from the PS, and that would then go into this section here, which would be replaced by stuff that would provide muon beams. At any rate, some of the details of trying to get that done. The layout of what this would look like is they have an extraction line, production target here with, could do about 20 kilowatts, I would guess. And then a beam transport, a little like the front end, but actually not nearly as high acceptance. And a chicane here, which is also part of our actual design, but it's used here to purify the beam going towards the demonstrator, and this sort of shows room for 5 cryomodules, which would give you more than a factor of 2 cooling. Again, so this is sort of one of their ideas. And this sort of shows us in a little more detail. I think this is a G4 beamline layout for this system. And the cell looks like this. It's 3 RF cavities, again, with 720 megahertz, a couple of high field magnet coils, and a couple of wedge absorbers. Well, 1 wedge absorber per cell, but they're about, it's about 1 meter, roughly about 10 cells per each cryomodule. Now, at Fermilab, we don't have any particular demonstrator plans, but we can try to think of what we might use starting from what exists at Fermilab. We do have 2 current really Muon beam facility based on, well, this is the so-called Muon campus. It's actually takes beam from proton beam from it turns out the recycler, not the main injector. Well, actually, the HF currently it's used at HF to produce for the G-2 experiments. It's put on a target here, and 3 GeV pions come out. They decay and then are put into the ring as muons. And so what's currently being being debugged is the beam for the Muon-E experiment, which is a proton beam, which is put into this delivery beam, which was the debuncher beam for antiprotons. But the protons would circulate in here and then be well, let's see if we got the direction right. Oh, the other way. And then be extracted here and sent off toward the Muon target hull at HF protons. So that's the current what's currently being done. And currently, this target hull and detector hull is being filled with equipment. Yeah. Oh, pardon? I'm sorry. Muon. Okay. It's HF protons coming in, but the target captures 50 MeV over C muons. So the transport selects out low momentum muons, which are then go on to the Muon target, where actually the average momentum at that point is 50 MeV over C, and the stopped muons then give you hopefully the Muon decays. Let's see. Okay, that's what exists. In the future, we are building, and it's PIP2 uh, uh, accelerator, which initially would be 0.8 GeV. It's initially going to be filling the booster to go to the main injector, but it will also there's a plan to use the beam from that to as a replacement for this HF beam in the future to go into here to produce pions, which becomes muons. Again, that's when PIP2 is finished, and but the other thing associated with that is right now the only known user of the PIP2 LINAC is this booster going to the to the uh, to the main injector for Dune, and that only needs maybe 2% of the potential capacity of the PIP2. PIP2 could initially do 100 kilowatt and can be upgraded to about a megawatt. And so there's a lot of potential beam that can be used for other experiments, but we don't have beam lines for them. We actually haven't built, we don't have funding to build the Muon transport there. But the idea is if, other than the feeding the booster, we would plan to have some other beam line going towards other experiments using PIP2. And the idea is to any rate. So this is sort of a zoo of where there are other proton beam lines we could use for various experiments, and I don't know. Actually, I'll probably point out a couple of them. I mean, certainly for targetry experiments, you might just use the high power beam from the main injector. I mean, basically trying to run Dune at the megawatt scale is a test of the type of targetry we need to do for the Muon collider, and there'll be presumably some sort of R&D program to support that. So that's one possible, at least compatible demonstrator. There are other beam lines that could be used, that might be attractive, or of course we can always build new ones. But again, I'll point out, there's an HF beam going to the booster neutrino beam that might be useful. And of course there could be new facilities. And so this is, and again with PIP2, we would like to have some other transport. If this is a transport going to the MUT experiment, that same transport could feed, say, some sort of pion. Oops, that went too far or wrong way. Let's see. Go back there. There is sort of the, I could see putting a pion, muon, or facility someone here for lower energy physics of any kind. I actually like you guys to fill in your ideas of what new pion, muon, or neutrino facility could be put in. I'm going back to the MUDE experiment where we're going to uh, uh, eventually, well, we use it for backward capture of low energy muon. So initially we'd put in 8-jet beams. Most of the beam goes forward. Now this experiment, the first order is similar to the front end for the Muon collider. Our dream machine, which hopefully captures all the pions and then all the muons, has a 20 Tesla uh, capture field, and this one has 4.5, but it is a solenoid with a target and attempting to capture a decent number of muons. Um, it's capturing backward for the MUDE experiment, and so this sort of forward production is quote wasted. I'm not sure if we could make it usable. It's kind of hard to rebuild the existing facility to try to use the forward part of that, or to try to bring the proton beam from the other side to get forward going this way. But at any rate, with this sort of things, we're capturing this 0 to 0.1 100 MeV over C muons. And it turns out, let's see if I got that. If you go back to one of the demos we will eventually want to do is the final cooling system. Turns out this, in final cooling, we actually slow the beam down. And for instance, halfway through this, we're at 50 MeV over C beam, which is at the energy of the beam, that the momentum of the beam coming out of the current MUDE source. So you could imagine putting a final cooling segment in that line, at least getting some muon beam through a segment. And this would be at some future date after maybe the MUDE detectors no longer used. And actually, that's maybe one of the things we might start thinking of. Again, this will probably be at least 10, probably 20 years down the road, but at that point, we could actually put in this is sort of like the size you would need for one of these absorbers and final cooling absorbers. Again, I don't know if that's really the best use of the of the space, but at least you could demonstrate part of the final cooling with beam there. Again, there's probably a better place to put it. And again, we've also thinking about what other experiments after MUDE could go in this beam line, and maybe other people have those ideas. What I'm trying to think is starting another beam line, sort of a bit like the MUDE, but forward production. Again, it's kind of a scaled back version of the Muon Collider front end, where we have a target. Maybe we could use an HEV proton beam, and I was thinking of the booster neutrino beam area as a possible place because it's at the right energy. It already has some infrastructure, and again, other people maybe want to use it for other things. But at any rate, as part of that system, you could put in a system like that, which is sort of a target, some kind of capture solenoid, again, not 100% capture, but maybe a few percent capture of all the pions and muons created, a decay line to get muons, which then could go into a cooling system, and what could be that cooling system would depend on our R&D needs. We could do another, cooling section from the baseline cooling scenario. And actually, if the first demo at CERN is at 704 megahertz, probably want to use the lower frequency scenario, maybe, or possibly cells from a higher field section too. Again, maybe not a long string, maybe a shorter string. But at any rate, that's sort of this ideas we might start to think about at the collaboration meeting. I've sort of thought there might be an idea of, instead of a linear cooling, develop a cooling ring where you have one section which is cooling system, maybe similar to the baseline, but with the recirculating transport that recycles many times through the same system, so you can get a multiplication of cooling. And that, again, if we could do that for more systems, we might do that sort of thing in the future collider scenarios. Another idea thought, well, if we've got all these pies, we could focus them into a stopping target for this mu plus E minus um, uh, electron capture muonium source. That might be an interesting experiment you might be able to do as a prototype for something like Nutristem. But there probably are much better ideas. I want you guys to come up with better ideas. At any rate, so this was a sort of a picture. Well, this is an old version of what a ring cooler might look like, but it's something to think about if we wanted to get a lot of cooling in one device. Anyway, so I'm putting this back up again, showing the current baseline scenario with all the things, some of the things which probably need to be done before you actually build a Muon collider, or while you're building the Muon collider. So then kind of leave it up for discussion for what you guys think of those can be done, should be done, you want to do yourself. Yeah. Yeah.
But
Well, okay.
is that, I mean, the fact that kind of the linear design is preferred to these versions,
Well, the
is it
linear
understood how to do
design,
that?
yeah, has the advantage. It doesn't. You don't have to extract or inject. So that's a major plus. Well, except you don't get the multi-turn cool. So, and again, that's something I sort of want us to look again a little more closely. We sort of didn't find a secure way to get in and out of a cooling ring. If we did, then we would probably go to a multi-turn system. And actually, there were some ideas for that, but I don't know.
I mean, when you say you didn't find a secure way to do it, like what's kind of the physics bottleneck that,
Well,
run
it has
into?
to be kind of fast fast pulse checker and matching optics. I don't know. We started looking at it. Probably, I suspect it could be done more for the later cooling stages after the beam's cooled a bit. And there are a few little tricks you can do in phase-space manipulation and would make one of those two, extraction or injection, easier. That is, if you inject at a different energy, but by the time it comes back again, it's at the recirculating energy. Yeah, so there's some tricks there you can use to get a little easy, at least one of the in and outs easier.
So in principle, you got linear cooling for the first part, do this, and then do final cooling?
Yeah,
Yeah, something like that, okay.
But I'm just sort of actually trying to get people to think, well, maybe maybe we can try to make this multi-step system a bit
More compact.
shorter and cheaper somehow.
But the kicker is just losses at that stage.
No, actually, but if it's a really good kicker, no. But I mean, just having it pulse fast enough, and over, well, the thing is, at least before the beam's cooled, it's a fairly large aperture that would have to kick over. And so at least in the initial parts of cooling, maybe it's not so easy.
Question is, if you build one that has high,
Yeah, actually for sort of a demonstrator of a lot of cooling, maybe you don't need as great efficiency on injection, and you take the injected beam, see if it cools. Now, if you just want to see if it cools, you don't even need to extract. You just extract it as it's going. But at some point, it'd be nice to be able to extract. Yeah, yeah. But actually, then there is a thought. Well, if you did this, and okay, maybe you weren't that efficient on injection, but you got a cooler beam out. Maybe there's an experiment that can use a cooled beam. Maybe that's been cooled by a factor of 10 or more.
How many people and how much time would you need to make a design that you would be prepared to ask us to build?
Oh, God. Well, I don't know. Actually, the example probably, it looks like a real design. Yeah. 20 odd. You need, I don't know. I'd say few engineers. And yeah, craftsmen, yeah. Well, I don't know, at least a dozen, I'd guess.
Dozen people and how much time?
No, I'd say it does 12 FTEs, I don't know, a year.
For 1 year?
Yeah, roughly. I'm just guessing. I'm not I haven't made budgets.
Well, you've got impatient people here, so
What's that?
we need to get these ideas out.
Yeah. Yeah. So yeah. So yeah. Well, it depends on which part. I mean, the actual there are various parts to be done here. I mean, there's also the simulation. You've got to design what kind of detectors you're going to use. Yeah. Well, I don't know. Yeah, the full demo probably starts at the $100 million scale thing. Any sort of significant demonstration other than say building an individual hardware piece, and that's say like an RF cell would be a few $1 million just by itself. Putting it into a beam, that's then any sort of demo is going to be at least 100 million. Look, say a multi-cell demo of any kind, probably more. Particularly if the DOE gets into the budgets or whatever bureaucracy. Yeah.
For your final slides or of your slides, you showed there are many items, technical items. It would be great to have a demonstrator on. I want to add a set of technology I want to demonstrate.
What?
What would be the minimal set of technology I want to demonstrate? That you still call it a meaningful demonstrator.
Really, all of them, but yeah, actually, some of them I would say, well, we don't have to build we won't be able to build the accelerator ring before we build the accelerator ring. So we'd have to start with building just pieces of it, magnets and RF modules of it. So yeah, and individual magnets as prototypes for at least half a dozen different areas. Let's see. Well, I probably left out some stuff.
Yeah. So if I have all of them, it sounds like way more than 100 million. So
Well, it's
yeah.
it's not quite as easy as it looks, but it's but a lot of it gets repetitive after you build a few of them.
Yeah. Okay. Thanks.
Yeah.
Or are they really just for
Well, that's a good. Nominally, we would be building a section of the cooling system that could actually be put into the final cooling system. To be honest, as designs evolve, when you get to the mass production one, it's probably somewhat different.
So what would the advantage be of using the B&B versus the beamline that goes to the Muon campus now?
Let me think. Yeah, let's see. I actually not sure. The thing is, I'm looking at well, at least it's buried more underground, which would help, but, and so on the other hand, well, I don't know, it's very old, but the A0 target area is used and it's been can use, I don't know, certainly can use 20 kilowatt beams and probably close to 100 kilowatt scale, but it's very old and where they're reconditioning it is, and maybe I'm thinking of the booster neutrino beam because it's newer and 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 but I actually, that was just sort of a thought. Yeah.
And then for like you kind of have the intermediate step of say like, okay, if PIP2 is completed and there was a beamline to like Muon 2E2,
Yeah.
since the energy is much lower coming out of PIP2,
Yeah.
you lose just on production
Yeah,
rate
you
for
could
Muon?
still continue that line. You get a fair number of pines and muons out of it. You could, again, a step down from what you want for collider, but you can definitely get enough for at least initial tests of something. Yeah. And of course, the other thing is that, at some point Fermilab will upgrade and put in
Booster.
well, nominally an HF booster replacement or a LINAC extension, and that would then could feed another beam line or it could be designed to use one of the existing beam lines. And yeah, I some of this detailed geography I don't know. I mean, some of the hardware that's being no longer will be used on for new me. I don't know. There's a target vault. Again, sometimes you might want to just close it off and never look at it again. But yeah.
At this list, maybe I have a question for you and for the room. Maybe it would be interesting to go through each bullet and understand if each of these components or parts of the demonstrator
Yeah, I wasn't expecting that.
could be interesting
Yeah.
or
Yeah, for
could have
instance,
any impact on other types of experiment or other projects that are being undertaken.
well, yeah, there's sort of RF tests of what gradient you can get with what cavities, what magnetic fields, or what sort of geography they could handle. That's each individual test is a fairly small size project, and but you want to then have sort of a RF test facility which can handle different sort of different types of RF systems we might here. So you'd like to have it. Well, it depends on what we decide to use for final, say, cooling or acceleration frequencies. Let's say if you might want 350 megahertz or 700 or other ones. And so there's a test facility at SLAC that can do a lot of that RF stuff. CERN has also it's sort of a thing, and would if the R&D continues, we'll have some stuff there. Some of the other labs, I think, I don't know, Daisy or the Clay, or I don't know if there's one in Italy too, Frascati maybe. That as RF test stands, they could test components. the target stuff is kind of, it's very compatible with what's being done for Dune and also for J Park, and sort of there's a general targetry collaboration that's looking at high intensity targets that can look forward some of our geometries as well. Acceleration, these fast cycling, well, assuming we go with keep with rapid cycling synchrotrons, then the very fast cycling magnets that we need to build for that need to be tested out, seeing if they can do the ramps they're supposed to, we would need. Cooling, yeah, okay, let's see. Yeah, that's in there, and there's some other ideas to look at. Magnets, everything here, the high collider magnets, again, those are kind of compatible with high field hadron collider magnets. There's a general program to build higher, 16 Tesla and higher field magnets. Again, building some in the geometries that would work for our collider ring or accelerator ring would be, try to get that on the program. That would be good. And, there's, of course, a lot of optimization work in there. And maybe new ideas to replace bits of this too.
So one quick question on the going from the map to the current IMCC cooling. You had a slide on that where you said they've significantly improved it, but there's still room because it's not matched.
Pardon?
You had the slide saying like for map and then going to the IMCC cooling design, they've made improvements, but there still could be more improvements based on matching. But I was just curious, what is kind of the main changes from the map design to the IMCC design that?
Actually, I think but I think one of the major changes, they're actually pushing to higher fields than the map design did. For instance, these last two segments here are nowhere near that. It's the final, at least what I've seen, the final cooling simulations are significantly better than what map had. And I, again, need to look at that. That needs to be looked at more closely to see how practical it is. I mean, and again, that's partly because they're using 40 Tesla rather than 30 Tesla magnets. So part of the improvement is the higher field. They are losing a bit because they went to higher RF frequency, but actually I don't see why they had to, because it's once you build them, you're going to be building in. I mean, we're using and 325 and 650. These are a little tougher apertures. So losing 10% there maybe. Might be better to go to a little lower frequency, but might cost.
I think the 700 megahertz makes it compatible with FT series as well. I think there's a synergy with FTC.
Yeah, but it's not.
Finite amount of money.
Yeah, I don't know. But if you're going to build that many of them, well, FCC EE is using 704. I thought they were. I don't know. I mean, it turns out, for instance, at least the accelerator at CERN, when they accelerated the rapid cycling synchrotrons, they were using 1300 megahertz cavities. So if you wanted it, and actually if you ever went to a multi-bunch mode, which you probably would consider at least, certainly if you ever hit the beam limit, then you would go to multi-bunch mode. Then you would want the cooling to be an integer or submultiple, and so you'd be happier with with staying. But that's if they used 1300 megahertz for acceleration, and but surprisingly they were able to get that at least on simulation to work for the RCS chain. I thought they need lower frequency, but yeah. So yeah, there's until you actually start building them, you realize once you start building them, you're building thousands, well, hundreds at least, of cavities, and people will follow your frequencies, not the other way around.
So how much is cooling scheme written in stone? And
Pardon?
how much is this cooling scheme that has been developed by IMCC and before by MAP, like let's say done, and is the thing arrives, and how much room is there still to explore? We've seen cooling ideas from
Well,
PSI or from JPAR.
That's a very good question. I don't have the answer.
Okay.
You guys have the answer. I don't know, or I hope you find. I don't know. I mean,
I guess it's also a question of timeline, right?
Yeah,
I mean, I guess we should probably start to push once funding becomes available.
yeah.
Start something concrete.
It's sort of a tough call. Do you stop for RD or just plow ahead with something you can build? It's always a tough choice.
Okay,
No.
then thanks a lot.